Hello, my name is Dr. Michael Okereke. I welcome you to this YouTube channel on getting started with modeling. The purpose of this video is on beam analysis. It's another series of videos I'm making about analysis of beams using finite element methods, and this particular video is dedicated to assessing the effect of end support on beams. In which case, what I mean is we are looking at the effect of how you're holding the support at the end, the beam at the end, on how that will influence things like the deflection, this deflection of the beam. So that's the purpose of this video. If this is the kind of content that you like, please do subscribe to this channel by clicking on the subscribe button, and also click on the notification button so that when contents like this are made, you will be the first to receive it. If you're also interested, in things that maybe I have not covered in my videos, do please suggest them, and I'll consider to make videos like that to help you with your getting started with modeling. So let's go straight to the video, to what we intend to do. So here is a PowerPoint slide that I've made to support this process. And basically what you see here is this is a beam that we're trying to model. It's a simply supported beam which is held pin support at A, and at D is called a roller support. It's a 40-meter long beam having an I cross section shown like this. So it's carrying a triangularly distributed load, with a maximum value at point D of 2000 Newton per meter. It's obviously going to be a 3D system made from a beam material. The properties of the steel are given like that. So in order for us to assess the effect of end support on the beam deflection, the first thing, we're going to look at these different case studies. So first, the case study of the problem that's stated at first, which is a pin support and a roller support as shown at A and D. Then the second case, we replace the roller support, the pin support at A, with a built-in support. So it's basically buried securely into the wall. And then we still retain the support at D, which is the roller support. And then finally, we model a case, for example, the column that runs across, the beam that runs across our roof. So it's both fixed at point A and point B in a pin support. So these are the three case studies that we're going to look at. And the idea here is after this, we'll take this information and plot a deflection profile for all three, and then compare them within ABAQUS to see what the difference would be. I just want to also tell you about how to model this triangular load within ABAQUS. So basically, we need to define, put the triangular load in an XY coordinate system, and here the expression that defines this would be y equals 500x, where x is at the position along the length of the beam. And how do we calculate the 500? Is basically the slope of that line, so which is the change in the y direction, which will be 0 and 2000, divided by the distance, which is 400. So that gives us 500. So y is equal to 500x. So that's what we're going to do. So let's quickly jump over to ABAQUS and get started with modeling. So here we are in ABAQUS. So what we're going to do right away is go to the parts environment. So you don't click on parts. So you get this. So I'm going to call this a beam. So it's going to be a 2D beam, deformable with a wire. The total length is 4 meters for the material. So I'll do 2.5 of that, or maybe 3 of that. So that gives me 12. So now I get this sketching canvas. So if I click right there and then go to the base, I can specify the start and finish point. The start of this line is 0, 0, and it's finishing at 4, 0. So that defines my line, which is the material that we want to model. So I right click and then cancel the procedure, go back to the base, accept. So this gets us into the environment where we now have our beam specified. So if I go back to the top here, so I'll create the material. So they click here. So my material is going to be made of steel, and I won't worry about density for now. So the elastic behavior of the steel will be made from a Young's modulus of 2e to the power 9 and 0.33. So that gives us the steel material. So let's think about the section, the profile. So we need to click on profile. So I'm going to call this my box profile, the I section profile, and we're going to select the I. Okay, continue. So just to check and see what our so let's get the dimension of this I section beam. So this is the I section beam. So basically the base is 100, the height is 200 meters, and then everywhere around it the thickness is to 20 millimeters, and it's quite symmetric to the top and the bottom. So we're going to use that. So based on that information, obviously the base is 200. So if we put the base, the height, and I is the center of gravity measured from the base. So if this is overall, h is 200, so this distance will be 100, but we're going to convert it in meters because we're working in meters. So our height is 0.2, the base is 0.1, the other base is 0.1, thickness 0.02, 0.02, 0.02. So that gives us the profile that we're working with. So what about the section? So we create a section, so we'll call it I section beam, and it's going to be made on a beam section. So it's already selected the only existing profile for us, and it's still, the material is steel, and then we have that all done. Okay, so that's basically associates. So we can then go back to the part at the top. So this is our beam. We need to associate this beam to the section that we have. So we'll do section assignment. I will click on section assignment, and then at the base here it says select the region you want to assign section. I will tick that, select, and click done. Okay, so it's associate that I section beam that we've created. Then the next thing we need to do is we need to give it a sense of orientation for this beam. So we click on that beam, and then it said select the region to assign beam. So we select that. This is fine, done, and select this default that it gives you. So click OK. So basically we've told this beam what directions we're interested in it. Just to visualize this beam to make sure it's looking right, so I'll go to the top and under view, part display option, and render the beam profile. Click OK. So this basically gives you the idea whether the beam looks the way it should be. Okay, is that exactly the kind of beam that we're interested in? It does look like the I section beam that we are interested in. So this is okay. Now, so we can leave it like that, and then do the meshing. So we need to mesh the domain. So double click on the mesh. So it gets you into the mesh mode. Click on that. So which is where you apply the global seed. It's predicting 0.4. Why not let me do 0. Maybe 1 or 0.05, something really small. So we select that and then click OK to mesh. So the domain is meshed. You can't see it in this window, so what we need to do is to go back and view part display option, the render. So allow it not to render, and then click OK. So you could see, then if you could see clearly that there is a bit of a render associated with this, which is good. So we're a bit of the profile. So this is okay. We're happy with that. So we've created the parts, created the sections. So the other thing to do is to create the assembly. So double click on the assembly. Okay, on the instance. So one stand is fine. Double click on steps. So I'm going to call my step bending load. The static general step is fine. You accept all that and click OK. So every other thing is fine. You could look at that, and what we're going to then do, you just move all the way and then find the loading. So I'm going to apply let's apply the load. Double click on the load. So this will be my triangular load, for example. So it's going to be created using a line load. The disputed load will be a line load. Continue. So at the base here, select the bodies for the load to be applied. So clearly I want it on that. Click done. So now what we have here, it says okay, fine, on this load, how do you want to apply the load? Obviously it has to be global. It is not a uniform, so we ask it. So we click on that to say okay, my triangular load function. So we want to work with an expression. Continue. So what is the expression? We found that to be 5,000 times x. Okay, so okay, that's not the description. So this is what we want. So 5,000 times x. So that defines our triangular load beginning from 0 to the end of the beam. So what is the maximum? Obviously the y direction load is what we want and it's acting downwards, so this is minus 2000. The x direction is 0, so we'll leave that. Okay, so we need to make a change again because we haven't applied that. So if you go on the triangular load, it doesn't look correct, it looks uniform, so we need to switch to a triangular load function, and then you could see, so it's starting from that and then increasing until you get it at the end of the beam, which is what we are really looking forward for this kind of problem. Okay, so now we've got a triangular load. What about the boundary condition? So if you go to the boundary condition, double click on the boundary condition there. So what we want here is, so let's start with fixed, or let's say pinned left. It's not a bending load, it has to be an initial boundary condition. We select displacement instead, continue. So this is my left, I select that and click done. So it's asking me how do I want to only restrain it in the x and y direction, because that's what a pin support will do. So boundary condition again. So now this is roller right. Select initial displacement, continue, select the right point, go to the base here, click done. So again, I only want restrained in the y direction. So okay, so this is done. So we're happy with that, so we can just test this. I'm going to call this case 1, and this will be pinned roller. Okay, continue. Okay, so we have pinned and a roller available here. So just to run the model, submit. So run the model, submit, and then see what we get to make sure that it's running. So basically, at what they say, analysis input file successfully completed. We look at the results. Okay, so how does the result look like? All right, so that's the deformation profile. If I go to view annotation options, so I want to increase the legend, and so that it looks a bit bolder. So maybe if we try 14. Okay, so the legend looks bolder. So we have, and then I also want to do view OD display option, and I want to render the beam profile as well so that we can see. So you could see we now have the deformed polymer, deformed material, and it looks okay. So we can animate it a bit and see. So I can also reduce the speed so you can see what's happening. So it does look, it's fixed, it's pinned at that point, and then at the other end is a roller support and it's nicely moving. So that looks all right. So now that we have finished creating the first case, so what we're going to do is we go to the model section again and borrow that model to create a duplicate for the other one. So I'm going to click copy number 2 and open that model, go to the boundary condition section, rename this. So right click and this will be built in left. Okay, for the second condition, we're looking to create only the built-in at the left. And if we double click on that, so this would have all 3 selected, because this is what happens when you're built-in. So there's no rotation, and then the 2 translations will not be. The roller support will still apply, and then we'll go back to create a job to represent this. So this job would be case 2, so built in with a roller, so let's call it that. Okay, and then we can submit that to run. So while it submits, so we'll go back to the top and borrow. Okay, so that's okay. So we'll borrow this model, create a copy of that, and then make this number 3. So this number 3 case would have 2 built-in supports. So I'm going to change this, rename that, and then I'm going to call it built-in write. Built-in write. Okay, and obviously we need to as well change it to both. Click on that, select all three to represent built-in. So we got both of them built-in. Then we just need to create the model, the job for the state case. So this will be case 3, and this will be built-in both. So both of them will be built-in. Again, we'll submit that to run. So submit. Now we finished the second case. So if I look at the results for built-in with the roller, so we could have a look at what the deform profile will look like. Okay, so we can see it's shown a deform profile. And then we'll go back and look at the third scenario. So it's completed built-in both. So we'll right click on that and look at the results, and make sure again it's showing a good simulation. So what we are going to then do is I'm going to create a way of comparing this. So click viewport create 1, viewport create 2, and then viewport style maybe horizontally. Okay, so basically this means that I'm going to do a comparison of these viewports. So still on viewport, you can then link all these viewports together so that at least what's happening in one will be the same. So now the first case here would be, so if I select at the top, the first scenario will be case 1. The second case, if I click there, the second scenario will be case 2, and the third scenario would be case 3, okay, which is already preset. So we've got all three of them set, and they are kind of linked in. So if you then click, so you can see that they show the same kind of behavior, and you can see the numbers that tell you some things. But what I really want to do is to make sure that I get them in a rendered form. So again, I'll go to the top here and click on view, ODB display option, render the beam profile. Okay, so that does that for the first one. You click for the second case, view again, ODB display option, rendered. Okay, and then click on the viewport for the third case, rendered in beam profile form. Okay, so we have everything now properly set in the way it should be. So if I click on this, you can do a rotation and study and see where the intensity of the stresses are and all that. So depending on the kind of boundary condition you have, there are different kind of intensities of stresses that you will get. I mean, the other thing to look out for is the size of the maximum von mean stress. So it's 9.5 here, 8.3, and 7.05, and these are all different due to the sort of end supports that you're using. So we're using the same I-section beam, but the end supports are all different, and that gives you a completely different response based on what you can see here. So that's probably one of the comparisons that you can make on that. So if I tile all of them again in a vertical manner, so if I tile vertically instead of tiling horizontally, then that gives you another view of how to look at the results. In particular here, I'm interested in the deflection values. So V, I mean U, which is the displacement in the direction of Y, which is a U2. So that gives you again the maximum deflection. So for the pins roller support is minus 8.3, about half of that for the built-in with a roller, and even quite a lot less than that for the two built-in values. So these are all different deflections that you see simply by changing the end support. And finally, we need to also show the graph of the deflection profile so that we can see clearly what the differences is in terms of all that. Okay, so the next thing to do is to consider the deflection profiles for this material. So we start first with the built-in roller support. So this is a built-in roller support and how it looks, not built-in both, pinned and built-in both. So we'll start with this, and we're going to work with it. So first, go to the path. So double click on path to create a path. So I'm going to call it case 1 path. Okay, continue, and then this add before. So to add before, we need to add the data for the graph, the data for the plot. So the start point and then end point. So this is the path that we want to use. I click OK. Then we then create an XY data for that. So if you double click on this XY data, so here we're creating it based on path, and the path is the case 1 path. So we want it to based on the undeformed, the original deformed data point. We want to work with that, and we include all intersecting points. So that means all the intersecting cells or nodes in that path, we include that, and the true distance, and our field output would have to be the displacement in the y direction. Okay, and then after that we apply and click OK. So we can then plot the graph. So if you plot the graph, it shows you what happens in the first case 1 path. Cancel. So with this data, so we could go there and say, okay, I'm going to save this data. So could rename it and call it case 1 XY data. All right, so we go back to path. So let's load the second case, which is built in with a roller support. So which we see here, create a path again. So case 2 path, case 2 path, which is what we see based on nodal list, add before the start position and then the end position. Okay, and then everything is clicked done. Then you go back. Okay, this is done. Fine. Now XY data based on that. Again, we want to base on a path, and our case 2 path is what we're interested. Deformed path points include intersecting point, true distance, field output, U2 direction. Okay, so if you plot that, then you get the full graph as well given. So you can save that data as case 2 XY data. Okay, so this is fine. Now we load the third case, which is the built-in in both direction. Okay, so built-in in both direction. So what we're going to do, again, create a path to analyze it with. So this is case 3 path. Okay, continue, add before start and finish. So this is fine, done. Okay, then XY data based on path, case 3, undeformed model shape is what we're using to link up all the intersecting points, field output U2, all done, and then you plot. So you get this case 3, and then you can save it as case 3 XY data. Okay, cancel. So we've got all that. So basically these are the 3 XY data. So you add them to plot, and it basically shows you that. Okay, or maybe I could delete. So what is that? So XY plot. Okay, so if I select all 3 of them and save plot, so you got just only the 3 of them, case 1, case 2, case 3. Case 3 is the red one. So that gives you the deformation profile for displacement profile for this structure. It may also be sensible thing for you to get this raw data into Excel. So you go to plugin, tools, Excel utilities, then basically everything on the current plot is what you want, and then you click OK. So what this will do is that it will load up Excel. You should have Excel in your computer. So this is Excel, so it gives you the data. So insert, so maybe this is time, case 1, time, case 2, time, case 3. So we could select all 3 of them to the end and then insert one of these plots. Okay, so this gives you the plot that we want, and then basically you have what you need. So case 1, case 2, case 3. Okay, so it's the other way around, so I've labeled it wrong. So this will be case 3, this is case 2, and this is case 1. All right, so you could then have a look at the result that you have and make sure that this is what you're looking for. Okay, so case 3, case 1, and case 2. So and this is the way it is. So basically the first, second, third, and plotted. You could then change it to a different distinctive graph set. So this is kind of what we were looking to. That brings us to the end of the video. If this is the kind of content you like, please again to subscribe to this Getting Started with Modeling YouTube channel, and click on the notification button so when videos like this are made, you'll be the first to see it. If again there is a video that you'd like me to make, put that in the comment section. I will consider to make that video to continue to help you to get started with modeling. Once again, my name is Dr. Michael Okereke, and see you in the next video. Bye bye.